So in the last video we saw about or in one of the previous videos we saw about the ensembles, and we discussed about different ensembles which are possible. And if you remember, ensembles do represents um, a kind of the different microstates possible for a particular macro state at the same instant of time. Okay, so instead of so it's a purely an artificial picture. So different microstates are presented simultaneously. So that is what the ensemble concept is. And when we are dealing with the statistical mechanical systems, as I told in one of the very previous videos, this statistical mechanics systems can be dealt in two different forms, either in the classical or in the quantum mechanical ways, right? When we are dealing the system in a classical regime, one of the formalism for the classical regime is developed on the basis of phase space. You might have learned already the phase space in your classical mechanics classes, right? So it's the same thing over here also. Here in statistical mechanics we talk in terms of the microstates and the macrostates. So so how does it fit into the phase space, right? I can tell that the microstates of a given classical system of course at a point time t can be represented by specifying its position and momentum at an instant for all particles constituting the system. So if I have a system like this, or I have an ensemble like this, I can always spot a point over here in terms of the Q and the P, where which I tell that this cross over here represents the microstate of the system at an instant t. So, and like in classical mechanics also, here also we are defining this microstate in a space defined by its Hamiltonian. Okay. So what happens now? The question is that so if there are n particles if there are n particles, there will be 3n position coordinates. Guess what? Q1, Q2 up to Q3n and 3n momentum coordinates represented by P1, P2 up to P3n. So in total, how much? Like in your concept of phase space you have learned, here also we have a 6n dimensional space. Which we call as the phase space, right? And now here I was going to ask you the question, what happens? Okay, so this point represents one of the microstates in the Hamiltonian. Okay. For my future discussions purpose, let me put this guy in a red thing. Okay. Hope you can see the red marking over there. Now, since this ensemble contains different microstates at the same instant, because that is central to the concept of ensembles, right? So there will be different microstates at different positions or different coordinates within this so-called ensemble. So this is another ensemble, another microstate, this is another microstate, this is another microstate, this is another microstate. 1, 2, 3, 4, 5. So I would tell you, so this all happens in the abstract world. So, but still I can tell you, actually I am representing here at least 5 elements of this ensemble. And of which this red one is one of the microstates or one of the elements of the microstate, elements of the ensemble. So my question, what happens as the time evolves to this microstate, for example, this red one? For example, for that one, what will happen? Right? What will happen? The answer is that this will move, or this microstates will change. There is a condition in which the microstate won't change, which I will tell later. So in the normal situations, this microstate will keep on changing. I can represent it like this. So I have taken this red one and after some time it moves over to here. After some time, if I look, it might have moved over to here. After some time, it may have moved over to here, and so on and so forth. So on and so forth. So if I take only this microstate over here, if I take only this microstate over here, this microstate itself will keep on moving within this space which is defined by the Hamiltonian. So do you know how can I represent this kind of a movement? Right? Do you remember your classical mechanics class? How can I represent this kind of a movement in the expression wise? So that information is given by your equations of motion, which you have learned again in your classical mechanics class. What was that? Qi dot is equal to dou h by dou pi, and pi dot is equal to minus dou h by dou q. So these are the two equations of motion which you learned for a phase space or a QP space in your classical mechanics class. So for this particle, for this microstate, which is actually representing one of the many elements of this macrostate, for this microstate, this movement is represented by this expression. So therefore I can tell that as time evolves, the Pi also moves in this surface, on this ensemble, or we call it a hypersurface. So what is the specialty of this hypersurface? It is naturally It is naturally limited by your Hamiltonian, which is actually equivalent to the h of hqp, which is actually representing then some kind of an energy sphere, right? Some kind of an energy sphere. So this particle cannot move. This microstate cannot move freely to anywhere. It will naturally be defined by the boundaries of this hypersurface, which is defined by this Hamiltonian. What else? So I have defined what is a phase space means by. One more thing to tell about is that which might be needed at some point of time. So I can always define a particular hyperstate defined by E, but it is always the case is that this energy barrier need to be filled, can be defined only within an error of E plus or minus delta by 2. So that is about the phase space, and the next video we will talk about something called the density function, which is an extension of which comes after defining system on the phase space. So the density function and the phase space and the derived density function are very important for the classical discussions on the statistical mechanics. Okay.